Hello world, it's Rational Pi, and how would you like to win $1,000,000? Well, all you have to do is solve an unsolved problem in science and math. Sounds easy, right? Well, it's not, because the Clay Mathematics Institute has what's called the Millennium Prize Problems, and that's what our rational list is going to be about today and for the next several episodes. So we're going to be going over each of the Millennium Prize Problems, and then we're going to outline a little more deeply what each one entails. And they include the Yang-Mills and Mascat problem, the Riemann hypothesis, the P versus NP problem, the Navier Stokes equation, the Hodge Conjecture, and the Birch and Swinnerton-Dyer conjecture. There's also the Poincare Conjecture, which has been solved actually by somebody, but they did not receive the $1,000,000. I think they just turned it down, in fact. But we'll be going over all of these. All of the problem descriptions are in the description below, and check them out if you want to. They are pretty technical, so if you do want to read them, just kind of be aware that it's not exactly the most entertaining of reading, but they are very informative. The one we're going to be talking about first, and we're going to be talking about this for a little bit, is the P versus NP problem. And what that is, okay, in computer science, there's what's called big O notation. So let's say an algorithm is O to the N, or O of N. What that means is if you have 1,000,000 inputs, it can solve it within 1,000,000 checks. So let's say there's O of N squared. What that means is there's 1,000,000 inputs, it's got to check each input twice. So it's going to be a million squared. And that's how long it's going to take to solve the problem. And that includes like bubble searching, where you have to take it and then move it somewhere, because then you have to check it twice. So that's how that's going to end up working. So it's going to check every single of the values in the million twice. So that's where the million squared comes from. And then there's logarithmic scales, log, whatever. If you want more information, big O notation, the Wikipedia for that is in the description as well. And what P equals NP is trying to solve is, let's say there's a problem that is really easy to check. But to get to that to get to that solution, it's ridiculously hard. That's what's called non-deterministic polynomial. And so, for example, you have a list of students, and you need to put them in rooms. But the dean or whoever is in charge says, all right, so there's some students that cannot room together. So by checking, okay, at the very end, okay, these two can be in a room, these two can be in a room, these two can be in a room. Okay, great. So you've solved the issue, and it was able to be verified very quickly. But all right, so everybody's in the room they need to be in, and there's not any conflicts. Great. But getting to that point is very difficult, because there's a huge amount of permutations that you could take to get to this final list. So, for example, if you have 100 students, you could have each student with a possibility of up to 99 other students. If you limit that to where the student can't be with 5 other students, then you still have to check 94 other students, and you have to do that for every single student. And then at the very end, if you end up with 2 students that can't be compatible, you basically have to go back and do the whole thing over again. So it's a complicated problem, but once you have the solution, it's easy to verify. And that's what's called NP. NP hard is if you're able to verify that a problem is as difficult as other NP problems. That's a little bit tougher to prove, but they have gone and proved some of these other algorithms and other problems to be NP hard. For example, the traveling salesman problem is NP hard. Why is it not NP? Because yes, it's easy to say it's been to every city once, but you have to prove that it's also the shortest path. That's why it's NP hard, because it can be compared to other NP problems, because it's not exactly easy to figure out, but the problem is finding it to be the shortest path. That's going to take you verifying against every other possible path, and if you have upwards of 50 to 100 to 10,000 nodes that you have to visit, it makes it incredibly difficult. And then NP complete is something that's both NP and NP hard. So the key here is if you're able to solve a problem that is NP in polynomial time, which is n squared, n cubed, whatever, polynomials, right? If you're able to solve something in polynomial time, then everything that's non-deterministic polynomial will then be able to be solved in polynomial time. And it's kind of tough to describe that accurately. So I would encourage you guys, if you're more interested, to read the description below, read some of the articles on it. And that's the thing, is that there's a lot of really interesting and seemingly easy NP complete and NP problems, but then if you really sit down and think about it, it's not exactly the easiest thing to figure out. One of those being finding prime factorizations of a number. That's not exactly easy to find because you have to basically brute force it to keep finding these primes. And that's the thing, is that brute force is very inefficient. So a clever programmer, if they're able to prove that one of these NP problems can be solved in polynomial time, then they themselves get $1 million. So we're going to be taking a look at some examples in the next video. If you have any questions, if you want some clarification, I'll do the best I possibly can to answer those questions. You can send me a message, comment below. I'm on Facebook, Twitter, whatever. I'm very interested in this subject. So we'll see how this goes, and we will go over the traveling salesman problem in the next episode.